Hi, my name is Mandy Pang. I'm the product manager for MySQL HeatWave. Welcome to the MySQL Autopilot session. Today, we're going to talk about how autopilots help automating MySQL in the cloud. We're going to give you an overview of MySQL Autopilot, and we're going to talk about the features and benefits of Autopilot for your OLTP, OLAP, and Lakehouse. And at the end, I'm going to give you a summary. Before I go into the detail of MySQL Autopilot, I want to give you an overview of MySQL HeatWave. MySQL HeatWave is a fully managed single database service that provides you for your OLTP, OLAP, and machine learning use cases. MySQL HeatWave is a tight integration with MySQL Enterprise Edition. We have a HeatWave engine that is an in-memory columnar storage engine that can be used for complex queries and OLAP queries that will provide order of magnitude performance improvements over MySQL. It is tightly integrated with MySQL. That means that there's no ETL that is needed for data that is stored in MySQL. Any of the updates of MySQL in the data in the MySQL will automatically propagate to HeatWave, so that you can always get the latest up-to-date data in HeatWave and be able to analyze the data with HeatWave. And also because of the tight integration, the interaction with MySQL HeatWave is the same as MySQL. So your existing MySQL OLTP applications, your analytic tools such as OAC, Oracle Analytic Cloud, Tableau, Qlik or Lookers can still use without any change in the application with MySQL HeatWave. We also provide machine learning for our end user to be able to train and inference data, MySQL data very easily. Similar to analytics, the tight integration allows us to be able to quickly load the data into the HeatWave cluster and then use that for machine learning purposes. And because our machine learning use of the HeatWave cluster, it makes use of the inter and intra node to provide very fast speed for machine learning capability. And on top of that, we have autopilots that helps to automate and improve the performance and scalability for OLTP, OLAP, and machine learning. So let's see how our autopilot can actually be able to do that. So just give you a background, MySQL HeatWave was introduced in November 2020, and then right afterward, we have introduced MySQL Autopilot. And since then, we have done a lot of new intervention in MySQL HeatWave, and then this continues with Autopilot as well. So here's a high level of what we offer in MySQL Autopilot. On the very high level, we have focused in 4 areas: system setup, data load, query execution, failure handling. As you can see here, the features that is highlighted in black is for OLAP that has been introduced since right after we introduced HeatWave in the cloud. And we have then since improved, like, for example, the machine learning model behind it. But right now, we have introduced new features, autopilot features that is targeted for OLTP and also our Lakehouse use case. So here is the MySQL Autopilot architecture. We collect all different statistics from the HeatWave service. So that includes the statistics from MySQL InnoDB, the HeatWave cluster, MySQL Optimizer, and all the query execution, all the statistics during query execution. And we do this by doing adaptive sampling, which allow us to be able to quickly get all the information that we need without scanning all of the data that is there. The next step is that since with the statistics, the type of statistics that we are getting is for preload, post-load, pre-execution, and post-execution of query. And because of the data that we collect, we can extrapolate all these statistics using a proprietary algorithm. And then with this statistics, we use our pre-trained machine learning model on the different area that we want to focus. For example, query performance, cluster capacity, network overhead, data load, etc. And so that we can predict like for the service, which in the 4 areas that we have just mentioned: system setup, data load, query execution, and failure handling. And all this machine learning model is based on our AutoML capability that allows us to be able to quickly train models offline, and then allow us to update models as our service grows. So now let's dive into what Autopilot for OLTP the features are. So one of the features that we is introducing is auto thread pooling. So in MySQL, there's a thread pool feature, but we have enhanced that feature to allow us to be able to do admission control to control the thread pooling so that it can be more efficient for OLTP. So on here, you can see that without auto thread pooling, when transactions comes in, they are kind of randomly executed. So there can be chances that some transactions get stuck behind a long running transaction, and that will make those transactions run much longer time. And then the other problem that we see with is that there can be resource contention because of how the different execution transaction is executed. Resources is not distributed evenly so that we can have a very even system. But with auto thread pooling, we basically admission control all the transactions and then arrange the transactions so that there is no resource contention, and which allow us to be able to provide a much faster OLTP performance to your system. So here is an example that we have experiment that we have done, like with a 10 gigabyte of TPCC, which is a well-known benchmark for OLTP. You can see that we are comparing with Aurora throughput. And as the number of concurrency increased with auto thread pooling, we were able to control the transactions, allow them to be able to run at a much higher throughput. At 2048 concurrency, you can see here that we are at 10x time faster, higher throughputs than Aurora. The next Autopilot feature we are introducing is auto shape prediction. So in OLTP, it usually takes a lot of time or experience for a DBA to find out exactly how big of an instance that it needs to satisfy the workload and provide the best performance for the OLTP scenario. But with auto shape prediction, we collect all the statistics from InnoDB query matrix and use that to predict the buffer pool size, the MySQL buffer pool size, so that we can adjust, we can provide suggestions and allow the end user to adjust the instance based on the current workload. So here's an example we have done. So we have a bunch of benchmarks that we run. So on the top 4 row, you can see we are using a small instance in MySQL HeatWave. We're using a 2 vCPU 16 gigabyte instance. And when we run the benchmark, you can see here the buffer pool heat rate is not at 100%. So when we run it with auto shape prediction, the ML model predicts that this workload is better off with upsize. So based on the statistics and the prediction, we predict that this particular workload will be better with a 8 vCPU and 64 gigabyte memory. So once the instance is upsized, we run the benchmark again, and then you can see on the right hand side, the throughput has improved, and then the buffer pool heat rate has also improved as well. It's important for the buffer pool heat rate to be at a much higher percentage, because you want all of your OLTP transaction to be running in memory and then without in the memory. So this shows that there is not a lot of IOs that is needed during the transaction, which means that you'll get better performance and then provide better user experience. On the second set of the experiment that we did is that we started off with a bigger instance with 8 vCPU and 64 gigabytes of memory. And when we run those benchmark, the auto shape prediction actually predicts that we don't need such a big instance to run this workload. So the auto shape prediction suggests a 4 vCPU and 32 gigabytes of memory. And as you can see on the right-hand side, with the result of the downsizing of the instance, the throughput is still about the same, and then the buffer pool heat rate is still about the same. What does that tell us is that the 8 vCPU instance is actually over provisioned. You don't need to such a big instance. So with the downsize, it helps cost saving, and then the performance still remain the same. So now I want to show you a demo of what I just described. So we're going to use one of the benchmark Twitter to show you this demo. So we're going to run this Twitter benchmark on a 2 vCPU and 16 gigabytes of memory of instance. So on the screen, you can see on the upper portion of the screen, we'll show you the throughput of the from the client perspective, how the throughput is, and then also the buffer pool heat rate. So on the lower left corner, I'm going to run the benchmark, and then on the lower right corner, I have MySQL client that is connected to the system, so that when we run the auto shape prediction, I can show you the result from the client perspective. So as I run here, you can see that it's running on the 2 vCPU instance, and then sorry. So as you can see on the graph, let me do this. As you can see on the graph, the throughput has been pretty low, and also the buffer pool rate is not at optimal rate. And now we run the Autopilot's auto shape prediction. As you can see here, that the prediction actually predicts that the buffer pool size should be a bigger buffer pool. You can see here is that it's predicting that it needs at least 28 gigabytes of memory. And if you run, the same on the MySQL client, you can see the same result here. So I'm highlighting it in red here. That's the Autopilot shape prediction is actually suggesting an upgrade, and so based on the buffer pool memories prediction, the 8 vCPU 64 gigabytes instance is chosen. And then now I can after the upgrade, I run the benchmark again. You can see in the red line that the throughput is actually much higher, and then also the buffer pool rate is much higher. And then once this benchmark is done, I also run the auto shape prediction again. And you can see it here that the auto shape prediction actually suggests there's no need for any change in the shape, as the buffer pool heat rate is good, and then also the throughput performance is good. So now next I want to show you is the autopilot feature for OLAP. First one we have is auto provisioning. So what auto provisioning does is that we use machine learning to predict the heat wave cluster size that is needed for your workload. Normally that is done by the DBA, and which is usually really hard to get a good sense of the size that is needed. Sometimes you get over provision and then sometimes it's under provision. So with auto provisioning, we sample the data that is already stored in InnoDB and use machine learning to predict the cluster size. As you can see on the table there, we have tried with TPCH, TPCDS, which are both well-known benchmark for OLAP, and with two customers' data as well. Our accuracy in the memory prediction is very high, so that shows that we are suggesting the right cluster size for the workload. The next one is auto data placement. So in MySQL HeatWave, we have a concept of data placement. Data is placed in the memory of HeatWave. So the way that with data, so you can with data placement, user can suggest how the data is placed in the memory of the HeatWave cluster. So the idea of data placement is that when we do query processing for queries such as join or group by, we want to make sure that the data from different tables of the same value are stored in the same node. This helps prevent the this redistribution of the data amongst the nodes while we are doing query processing. So this is usually very difficult for an end user to understand. One is because they may have a lot of queries, and then we don't know like which one is the most time consuming in terms of like shuffling the data, or what kind of query that can benefit from using data placement. So what we have done is that we have developed a machine learning model that will look at the past queries that is run in the system and look for any opportunity for improvement in terms of how we store the data in the HeatWave cluster, and provide suggestions to the end user for the data, and if there's any data placement suggestions to improve the system performance. So as you can see on the graph here, the goal is that we want to prevent as much as possible for data movements during the query processing so that we can reduce the networking time and hence improve the query performance. And if you can see on the bottom table there, similarly, we have done a TPCH 1 terabyte and 4 terabyte data set, and both we have seen from the prediction and the actual improvement, it has like more than 25% improvement. The next feature that we have is auto encoding. So in HeatWave for string column, we have a feature, we compress the string columns in two different ways. One is through dictionary, and then one is through variable length. So with dictionary, the dictionary code is actually stored on the MySQL node. And then with variable length, the data is actually stored in the HeatWave cluster memory. The main difference between the two is that when you use, it's the function that we support. So variable length supports more functions, and particularly for string columns using like string manipulation, or using string columns for joins. But there's also advantage of using dictionary is that if there's queries that do like a full scan on the column, for example, dictionary is going to be much faster because the data size that we need to scan is just the dictionary code is much smaller, so that the scan can go much faster. So again, this is very difficult for end user to decide which column to use encode and to use dictionary encoding, and which column to use variable length. Is really depending on the query that they use, and also how much memory that they want to save. So in that sense, we have auto encoding, which we look at similar to the auto data placement. We look at the past query that has been run on the system and look for any opportunity again to improve the performance based on improve the performance and also memory usage for the system. So here with auto encoding, we with the TPCH 30 terabyte data, we are able to see that when comparing to so the top one, the memory optimized encoding is actually having an experienced user to do handcraft encoding versus using auto encoding to do the suggestions. You can see that actually auto encoding is actually using the suggestions from auto encoding. The runtime is actually 2 times faster than a hand coder encoding. The next one is auto query plan improvement. So with this feature, we collect statistics of the queries that is run in HeatWave. And if there's a query that have a construct which is similar, in this case on the slide here, you can see that on the bottom there's a table A join table B, and on the right hand side this query has also column table A join table B, but then the top construct is different. But the advantage of this feature is that even though these two queries are not the same, but they have similar construct, we can use the statistics that is run on the left-hand side query and use that statistics to help improve the query on the right-hand side. So if you run the query on the left-hand side first, we collect the statistics and we use that statistics to help improve the query plan for the right-hand side query. So when the right-hand side query first run, it will get a better query plan and hence a better performance for this query. So with a 24 terabyte TPCH and TPCDS datasets, the performance with this query plan improvement, we can see that the performance is actually improved by 40%. Another one is auto scheduling. So we understand that queries can have different runtime, but then they can come in at any time. So if in a normal situation where usually you have more like a first come first serve system, if on the top you can see that on the top right hand corner is that there's the baseline. If you have a first come first serve system where you have different query that comes in, Q3 will suffer from Q1 and Q2 because this Q3 needs to wait, and Q1 and Q2 actually runs much longer than Q3. But with auto scheduling, we automatically predict the query runtime and prioritize the shorter query while not suffering for the long running queries. So on the bottom, on the next graph, you can see if Q3 comes in right after Q1 with the same as Q2, we will prioritize Q3 to run first so that the overall performance of the system has improved with the shorter query be able to run much earlier, while the longer query will need to wait for the shorter query to run. But from the overall perspective, because the longer query is going to run much longer, so the impact on the longer query is not as much. And you can see on the bottom two tables there, with a mix of long queries and short queries, the overall short queries that is run, you can see the elapsed times has improved about 45%, and the elapsed time for the long queries, in the impact on the elapsed time is actually only 6% for the long queries. So with these, the overall performance of the whole system across all the queries is improved. So now I want to show you a demo of using the not just actually the data placement, but also with data encoding, how the two combined together can improve the performance of the system. So as you can see here, right now I'm using the default setting without any encoding and data placement. I'm running those 4 queries. So I'm on the top with the table, I'm listing the runtime for each of the query, and then the total time. Now I want to run auto encoding. After running auto encoding suggests there's changes that can be done with encoding. So we make the changes and run the queries again. And you can see here the total time is actually running much faster, and then the improvement is about 2.6%. And now I run auto data placement to see if there's any suggestions. And then after running that, and then you can see the overall total time has also improved. And comparing to the default settings, the overall is about 3 times faster with Autopilot. Oops. Okay. And then the next one I want to just talk about is Autopilot for Lakehouse. So MySQL Lakehouse is introduced at Cloud World. So the way that we approach with this Lakehouse is that, first of all, when we first have MySQL, and then later on we have added MySQL HeatWave, which is targeted for analytics and mixed workload. And then after that, we added machine learning capability into MySQL HeatWave. And now the idea of the Lakehouse is that we want to be able to query data that is stored on object storage. So data such as CSV, Parquet, like backups from Redshift and Aurora, be able to load the data directly from object store into HeatWave without going through MySQL, so that this data can take advantage of the high performance of the HeatWave cluster and be able to analyze data very quickly. And then the last one is the Lakehouse. What that means is that you can use MySQL HeatWave to query data that is stored in InnoDB, MySQL, and also in the object storage. This allows us to be able to handle a much larger data sets because you can store a lot of data on object storage. So the Autopilot for Lakehouse here's the list of the features that we have designed for Lakehouse. So the first one is auto schema inference. As most of the time, the data that is stored in the object storage has no schema, so we will be using a machine learning model to predict the column data types so that we can provide suggestions for tables definition. The second one is adaptive data flow. So because of the integration because we need to get data from object storage, and also HeatWave also stored a copy of the data of the HeatWave data onto our own object storage layer. Having requests to object store it depends on the data object store performance, and then we adapt to that, and then this allows us to have much better performance and better reliability. And then number 3 is adaptive sampling. So adaptive sampling is used throughout different features in Autopilot, but this is especially important for Lakehouse because the target data size for Lakehouse is in the hundreds of terabytes. So this allows us to be able to quickly sample data in the object storage and then use it for other features in Autopilot. Number 4 is auto provisioning. As I mentioned earlier in the HeatWave use case or OLAP use case, auto provisioning allows us to be able to predict the number of nodes that is needed, and we have enhanced that for Lakehouse so that we can sample the data, the raw sample data, and then be able to predict the memory needed, and then also the cluster size that is needed. Number 5 is auto load. So we also use machine learning capability to basically predict the load time, and then so that you can and also load scripts so that you can easily load the data from object storage into HeatWave. And then last one is the auto query plan improvement, similar to the the autopilot feature on for OLAP. We have also expanded this use case so that to cover a much bigger data set and also for object storage. So just kind of dive into a little bit more on auto schema inference. So the idea here is that we want to sample the data that is stored on the object storage so that we can predict or infer the data type on the data that is on object storage. We are able to inference this really quickly because we run the inference in parallel. And also we integrate with auto load so that in one go, when you try to load the data, we'll provide you the schema prediction, and also you can get the load scripts to load the data into HeatWave. The other one I also mentioned briefly earlier is that the adaptive data flow. Basically, if you look at the graph on the bottom, the left-hand side, the blue line shows the object storage bandwidth. So it can change according to based on time and usage on the network, or the if there's any other users using the object store as well. So it fluctuates. If we using the same request rates into the object storage, the disadvantage of that is that if the bandwidth or the object storage request has been saturated, we will get error from the object storage, which may end up be affecting our service, making it unavailable. So with adaptive data flow, we adapt to the performance of the object storage to adjust our request weight. This allows us to be able to reduce the number of errors and improve availability, and then also improve the overall performance. So with that, I'm going to into a summary. So this is just to give you a summary of what Autopilot is. So we have talked about Autopilot for OLTP, for OLAP, and for Lakehouse. And the area that we focus on is system setup, data load, query execution, and failure handling. And there are two types of autopilots that we have. One is an advisor, so it's focused on the system setup and data load area, where basically we don't automatically adjust the system. We provide suggestions to the end user, and then it's up to the end user to take the suggestions. And then the bottom part is automatic. So whenever we detect there's opportunity to improve the performance or the availability or the scalability of the system, we will automatically adjust without any user intervention. So with that, I am concluding my session, and thank you so much for your time.